Okay, so let's now start with our nebula. And this nebula, this molecular cloud, so another name for a nebula is a molecular cloud, is going to be 10 light years in diameter. So the current size of our solar system is about 40 AUs. So the distance from our sun to Pluto is about 40 astronomical units. The distance from our sun to our closest star, Alpha Centauri, is going to be about 4 light years, which is about 10,000 astronomical units. So this thing is going to be 10 light years in diameter. The original cloud that is going to form stars is going to be about 10 light years in diameter. Okay, now it's going to start to collapse because of gravity. So one way or another, there was a nearby supernova, or there was a solar wind, or it collided with another cloud. Something happened that it compressed the nebula so that the nebula is beginning to collapse. So the first thing it's going to do is it's going to fragment into multiple gas clouds. And then it turns out that each of those gas clouds is going to fragment into even smaller gas clouds. Each of those individual small gas clouds is going to turn into a star. So stars are born in clusters. Normally somewhere between a dozen, maybe up to 100 stars could be born at the same time from one gigantic gas cloud. Okay, the next thing that's going to happen is that as the radius is decreasing, the force of gravity is increasing. So we already discussed that first one there. So because of the law of gravity, big G m1 m2 divided by r squared, as the radius is getting smaller, the force of gravity is increasing. Okay, now the second statement says that pressure, P, is a force divided by an area. So that was the definition of pressure. So if F is getting bigger, then P has to be getting bigger. So as the gas cloud is collapsing, the pressure inside the gas cloud is also increasing. And then the last statement is the ideal gas law. So pressure times the volume of the gas cloud has got to be equal to the number of molecules of gas that are inside the gas cloud multiplied by its temperature multiplied by a fundamental constant of nature. Now, we don't care about that fundamental constant. All I want you to notice is as the pressure is going up, the temperature is going up. So as this gas cloud is collapsing, the temperature of the gas cloud is increasing. So keep that in mind. All right, now the next thing that's going to happen is as the fragment contracts, collisions between the gas particles cause a disk to form, which eventually becomes the planets. Does that sound familiar? Yeah, we already talked about this in unit number 2 when we talked about the formation of the solar system, and we said that as the gas cloud collapses because of collisions, it flattens into a disk. Well, we don't really care about the disk. What we care about is what's going on in the middle of the disk. That's what's going to become the star. So we don't really care about the disk so much, but that's where the planets are going to come in. Okay, then the next thing that's going to happen is it's going to start to develop a magnetic field. So we said the sun has a magnetic field because the sun is spinning, and so those electrical particles are going around and around, and we said that electrical particles, when they're moving, generate magnetism. So that the Earth is spinning, and so the electrical materials going around in the core of the Earth is causing a magnetic field that is going to look like this. Okay, the sun is spinning and it has a magnetic field. So this object is also going to have a magnetic field. And at first, it's going to have a very powerful magnetic field because as it's collapsing, according to angular momentum, it's got to be spinning faster and faster and faster. Just like the ice skater. When the ice skater brings in their arms, they spin faster and faster and faster. So as this protostar, this thing, it's not a star yet, but it's getting hotter. So this thing that's going to become the star is spinning faster and faster. Its magnetic field is getting stronger and stronger. Well, something really interesting happens because surrounding the star is the disk. Okay, so here's the disk part, and this is going to eventually become the solar system. And so this magnetism begins to interact with the particles that are in the disk. And so it gives some of its spinning motion. So this thing starts to slow down. The star, the protostar, begins to slow down. And as it slows down, something else must speed up in order to conserve momentum. And it turns out that's the planets. So these objects out here will begin to spin faster because this thing begins to spin slower. And it all has to do with its magnetic field. Okay, the next thing that's going to happen is the temperature is now going to get up to 10,000 Kelvin. So what was the temperature that it started with? So we said in outer space it was like 4 Kelvin, and then in the nebula it was like 30 Kelvin. Okay, so as it is collapsing, the pressure is going up, okay, and as the pressure goes up, the temperature is going up. So now the temperature is up to 10,000 Kelvin. And the hydrogen and helium atoms become partially ionized, so it's now hot enough that the atoms of hydrogen and helium are starting to lose their electrons because they're becoming ionized. And when this happens, they start to flow in big convection patterns. So inside of this thing, which now has more of a spherical shape to it, it's still not a star. It's still a protostar, but it's now hot enough that it is convecting on the inside. Now, can you think of something in our solar system that has a temperature of around 10,000 Kelvin in the core and is convecting and is made of hydrogen and helium? That's Jupiter. So you can think of Jupiter as being a failed star. If Jupiter had been bigger, it would have ignited. It would have turned into a star. But it just wasn't big enough to get the temperature high enough to ignite. So all that Jupiter is doing is convecting on the inside like that thing right there. All right, so now let's go to when the temperature of the core reaches 1.5 million Kelvin, all of the atoms are now completely ionized, and then radiation is the easiest way for the heat to get out of this star. So notice in the middle part, so that's where the temperature is around 1.5 million Kelvin, the heat is trying to get into outer space via radiation. And then when it gets to that red part, the temperature has now dropped to about 10,000 Kelvin. So in that part of the star, it's now convecting. Okay, and then it's still getting hotter. So it's still continuing to contract. It's still getting hotter and hotter. and now it has reached 10 million Kelvin. So when the temperature reaches 10 million Kelvin, the hydrogens smash together, so that's nuclear fusion, and starts turning into helium. So now the star has turned on. So now we have thermal nuclear explosions. We now have a real star at this point. Now, you don't need to worry about this, but it stabilizes at about 15 million Kelvin. So don't worry about that. But so you do need to know the number 10 million Kelvin. So that's the temperature at which you need to have in order to slam the hydrogens together hard enough that they will fuse into helium. All right, now take a look at that picture. So you have a core at around 15 million Kelvin, which is currently fusing hydrogen and helium. Then surrounding that is a radiative zone, and then surrounding that is a convective zone. Does that sound familiar? That's our sun. So we have just manufactured all the different layers inside of our sun. Well, I just wanted to show you here. Now, don't worry about it, but I wanted to show you that some stars behave differently than what our sun does. So what we have just witnessed was the birth of one of those orange stars there that has a mass between 0.5 and 1.5 times the mass of the sun. So our sun would have a mass of 1, so it falls into that category. But then you'll notice that off to the left, you got the little guys. So these are going to be stars that have a mass of less than 0.5 times the mass of the sun. And what do you notice? Well, you notice that they're still red, and that's the core. So that's the place that is converting the hydrogen into helium. But notice that the entire star is convecting. The entire star is fusing helium. And then if you look at that blue one on the opposite end, these are going to be stars that are greater than 1.5 times the mass of the sun. And what do you notice about that picture? Do you notice it's flip-flopped? So it still has a core, just like our sun does, where the nuclear explosions are taking place, but then surrounding it is a convective zone, and then surrounding that is a radiative zone. So it's the exact opposite of what our sun is doing on the inside. So the mathematics of that is pretty difficult to understand, so I encourage you to go to Google if you're interested in this and find out why does it look different on the inside. So all I want you to be able to do is how did our sun develop? So what was the processes that developed inside of our sun? Okay, let's take a break. When we come back, we're going to take a quiz over what you have learned.